Hi folks, thanks for joining in. I'm Prabhas Srivadana from WSO2. Hope you can hear me well. Can someone please ping on chat? Okay, great. Okay, thanks. Yeah, so today this is our sixth IAM4 developer meetup, and we are going to talk about securing service interactions over HTTP, gRPC, and Kafka. And so we invited two speakers. Kasun is the product lead of WSO2 Enterprise Integrator, and Nuwan is the product lead of WSO2 API Manager. If you are new to WSO2, WSO2 is a company which produces a set of open source products, all released under the open source Apache 2 license. Kasun also published, he has published 3 books. The latest one is gRPC Up and Running, published by Unary. So he's a subject matter expert on gRPC. And Kasun and I co-authored the book Microservices for the Enterprise, I guess in last year, published by Apress. Nuwan authored the book Microservices Security in Action. He co-authored that with me. And this will be out hopefully by August. It's going through the last stage, proofreading, and early August, if everything goes fine, the book will be out. A couple of housekeeping items before we start. So all of you are muted, but in case if you have any questions, feel free to unmute and speak up, or else you can use Zoom chat. Yeah, so with that, I'll hand over to Kasun, and the flow would be Kasun will give you an overview of gRPC, Kafka, HTTP, and why you should pick one or the other. And after that, we'll hand over to Nuwan. So Nuwan will take us through different security techniques that we can use to secure communications that happen over Kafka or over gRPC. Over to you, Kasun.
Yeah. So I would like to start the session with giving an overview of gRPC, because I think most of you are familiar with HTTP and Kafka for the most part, but I'll talk about all 3 technologies and compare and contrast them and how you can use them in a typical microservices deployment. But let me start off with explaining what gRPC is. So at very high level, it's an inter-process communication technology. So when you are developing cloud native or microservices based applications, you usually develop them as distributed applications. So these distributed applications needs to communicate it with each other. So that's where all these inter-process communication technologies coming into the picture. So unlike HTTP or REST-based communication, gRPC provides you a way of invoking distributed service as easy as making a local function call. So that's the, in fact, it's a core concept behind the RPC technology. So gRPC is a way to sort of modernizing the legacy RPC so that it works with all these cloud native and microservices related technologies. So at very high level, the foundation of gRPC is purely based on a contract first approach, where you always start with a service definition, a service contract, right? So you define the service, so you convert your business functionality into a service definition. And from that service definition, you can derive server side and the client side. So I'll go into the details of how you can implement server and client. And the key difference when we compare this with the HTTP or REST is it uses a protocol buffer as the underlying message format, which is purely based on binary messaging protocol. And also it use so based on the contract first approach, as you can see, you can generate your server side with a specific programming language, and client side can be totally different programming language. So it's this it fosters the polyglot nature of cloud native application. So it's becoming very popular because of that reason as well. Now let's look at service definition example. Now, suppose we are designing the same use case. We want to define a product service, product info service, and we want to develop the server side and the client side. So the first thing that you would do is you define the service definition. Basically, the business functionality here is to have a service that caters the product info capabilities. And we have two remote methods, add product and get product. So this is defined using a protocol buffered service definition. So, so gRPC uses an extension to the protocol buffers so that it can incorporate all these service definition as part of a proto file. Right, so you define your service and you have your service definition, remote methods, and different data types that you would use in your methods. And so that this is all you have to do when it comes to defining the service. And some details about the protocol buffers. It's a language agnostic, platform neutral data serialization format, which uses binary protocol. So it's a very efficient data serialization format. That's one of the key reasons behind the high performance nature of gRPC. Now you define the product info proto file, and then the next step is to develop your service. Now suppose that for the service development you are using Go. So what you have to do is you just have to get the service definition file and generate the server-side code. So as part of the server-side code, it generates a service skeleton, which basically provides all the abstractions related to wire level communication, HTTP2 bindings, protocol buffer data serialization. All those things are transparent from the developer. So as the developer, what you are simply doing is you are implementing some methods, some remote methods. So here you, in this Go code, you are implementing add product method and then get product method. So that's the service side of the application. Now you want to run this service inside a server, right? So you want to host this on a particular host and a port. So that's where you create a gRPC service. So this can reside in the same file or in a separate file if you prefer. And you simply have to create a gRPC server using this syntax. And then you bind that, you basically register the service that you already defined at the top with the new service that you are with the new server that you have started. So that's the most simplest approach of creating a gRPC service. And the client side is also very similar, right? So client side is responsible for connecting to a gRPC service and basically invoke a remote method. Now here what you have, what I have is a Java side of Java code of the client side. Basically you generate code for Java and then you use basically use the generated client side stuff to invoke the actual remote service. So similarly, what you can see is as the developer, you only interacting with these abstractions, right? So here you have stub get product, just sending the product ID as the parameter. So as part of the channel builder, you are giving the actual address of the service. So that's all you have to do as part of the service side and the client side. Now, since now you have a good understanding about the foundations of gRPC, let's look at some of the key advantages that gRPC brings into the picture. So owing to the binary protocols that it uses, it's efficient. So compared to HTTP, which is text-based, it is very efficient. And also having well-defined contracts. So contract is a mandatory thing when you define when you develop gRPC applications. So it's a plus point actually. So you don't really have to worry about invalid data types. There are no any major security related false coming in owing to the leaks in the data types. So having a well-defined service contract is easier, and also it's drastically decouples the client side and the service side. So and also, since this is strongly typed, there is always a type defined for any particular argument or parameter that you passed as part of the remote method invocation. So it's very type safe. And as I mentioned earlier, this is polyglot, which means you can use different programming languages. So you can, even within a single organization or a single project team, you can use multiple programming languages to implement your client side or server side. And one other main advantage of gRPC is the duplex streaming. So it is not purely request response only. So if you want to have some streaming scenarios, either it can be server side or client side or both. So you can implement those streaming scenarios as well. So I'll cover some of these use cases in the upcoming slides. So, and being a cloud native computing foundation project, it's getting a lot of traction from the Kubernetes community as well as the rest of the cloud native ecosystem. So it's a, so for example, if you want to build observability capabilities into your gRPC service, all those things are out of the box capabilities are available in Prometheus, Jaeger, and other tools. Okay, so now with that, I want to explain some of the key messaging patterns of gRPC. There are 4 main types. So I'll quickly go through all those 4 types. So the first and the most simplest one is Unary or simple RPC, where client send a single request to your remote service and you get a single response back. So the use case is you send a get order. You basically invoke the remote method get order and you get the order details back in a single response. So this is the service definition. So it's very straightforward one, similar to the one that we have already discussed. So this is the service implementation and the client. Right? So it's very simple. And then you can do service streaming RPC. So that's where you invoke a remote method. So basically, once you invoke the remote method, then server starts sending back a sequence of response. So we can call it a stream. And so after getting the client request, server can start streaming all the responses back to the client. So this is known as server streaming RPC. So after sending all these responses or messages in the stream, the service can make the end of stream by setting a particular flag. So basically, server marks the end of the stream at this point. And the service definition for this scenario is slightly different. Now you can see here is my RPC method, search order, and I'm only passing one single parameter, the query, and it returns a type, but it's a stream. So stream of orders are returned. So when it comes to service side, what you can see is you, as part of the service implementation, you get a stream. So once you do the code generation, so in this Go code, you can see there's a stream of objects coming in. So using that stream, you can send multiple order objects. So this, the business logic may differ. The way that you develop the business logic may differ from one programming language to the other. So in this Go example, it's somewhat straightforward. You just get a stream and send some orders back. But in Java's case, you have a separate interface where you have multiple methods to catch this stream of events. So the client side is there's not much of a difference. It's just a single invocation. And in the client streaming, it's the opposite of service streaming. So that's where you have you're sending multiple client messages to the service. So here I'm sending a series of orders, sequence of orders to the service. So server can actually decide responding even after receiving one request or one message, or after receiving all the messages in the stream. So it can either look for the end of stream of this update order, or even after receiving the first request, it can send in the response back. So as you can see, it's again very straightforward. You just do the update order. So there's a typo here. It should be update order, and it returns a single value. Right. So now in the Java code, the service-side code of the Go sample, you can see. So there's a receive method till the end of the stream, end of this update stream. You are basically sending. You are basically looping through all the messages in the upcoming client stream. So in the client side, you can, similar to the server side example, you just use the stream and start sending all the different orders to the server. Then finally, you can do the close and receive. Okay, so.
Kasun, there's a question on Zoom chat. Can you see the Zoom chat now?
Yeah, let me check.
Or else I can read out. It's from Alan. It's
Yeah.
RPC synchronous. In other words, does the client block waiting for a response?
So there are multiple APIs, the synchronous and asynchronous APIs. So you can, for the most parts, you can send a request and wait in the blocking nature. But there are, in particular, these streaming scenarios, it's mostly non-blocking. So once you send the stream of messages, you can receive them at any point, because it uses the same HTTP2 connection. Yeah. Are there any other questions, Prabhat? Or?
No, that's it for the moment.
Okay, okay. Yeah. Okay, so in the bidirectional streaming case, there are, it's a combination of client-side and the server-side streaming. So it's slightly complicated if you try to map this to a use case. Now, the use case I used here is, so you are sending multiple set of orders, like sequence of orders, and based on the various order details, you can generate, the order management service can generate different shipments. So shipments, there can be multiple shipments. So means that means that you'll have multiple shipments, which means a stream of shipments. So that are actually returned back to the consumer. So when you are defining something like this, you'll have a stream in the request parameter as well as the return parameters. So what we are receiving here is a set of order IDs, stream of order IDs, and stream of combined shipments. So this is how you define your service definition. So the logic can be drastically different based on the use case, but the key idea here is that you have a loop from the service side as well as the client side. So basically, you can basically have a loop and start reading all the incoming orders, and then based on the business logic, you can send different, you can create different order shipment objects and send them using the stream objects. And in the client side, this is related to the question that was asked earlier. So in the client side, you can invoke the process order method and then start sending different order IDs, and the responses from the server can be received in a different thread. So here we are creating a different thread, and so basically we are receiving all the responses asynchronously using a Go routine. Right. So I think this may be a little complicated if you are trying to map this to a business use case, but the key idea here is that you can do streaming at both client and server side. Okay, so now let's try to map this into a business use case, the application of gRPC. So the key idea behind gRPC, at least the initial usage of gRPC is for internal service communication. With the inception of gRPC at Google, it was initially used for a lot of internal service communications. There are few gRPC services exposed as APIs to the public, but owing to its high efficient inter-process communication nature, it is still being used as an inter-process communication for internal services. Now, if you look at this example, here we have multiple services implemented using different programming languages. Now you can see there are a lot of internal services that uses gRPC. So for most of the request response scenarios, you can use gRPC, or even for some streaming scenarios, you can use gRPC. But when it comes to exposing these services, you may expose them as REST full services, or even services such as GraphQL, right? So, but the actual backend services may be implemented using gRPC. And when it comes to Kafka, not all services are synchronous, like request response based services. There are a lot of event driven scenarios in your enterprise. So you can simply map a message broker into those scenarios and implement all those event driven communication using message broker. So, so what I really want to emphasize here is that gRPC is it's not a silver bullet, but the coexistence of gRPC with other technologies is the most common and most pragmatic way of adapting it. And if you want, you can also expose them directly to the external world as a pure gRPC service through the API gateway. So some of the, in fact, most of the examples I explained today are available in this website, grpc-up-and-running.github.io. So you can find all Go and Java examples of all the different use cases I explained. And in the book, we have multiple other scenarios like advanced gRPC communication patterns, how to use these in production, best practices, as well as different observability tools available for gRPC. So feel free to check it out, and if you have any questions, feel free to drop us a note in the meetup, or feel free to email me as well.
There's a question, Kasun. So Alan is asking, what is the failure model, particularly lost or delayed messages?
Yeah, so that's mostly related to the internal implementation of the gRPC protocol. So that's I would say, since it uses HTTP, so most of the delivery guarantees are bound to the HTTP2 protocol. So basically, it uses HTTP2 stream. So whatever the message is coming in a stream, there is a guarantee. But I won't say that gRPC ensures the guarantee levels as with any other messaging protocol, such as AMQP or Kafka. We don't have that level of guarantee, since this is pure request response method. It always fosters the idempotent messaging. So when there's a failure, you just have to retry. So that's where all this retry and load balancing, circuit breaking being built into the gRPC as part of the ecosystem.
There are a few more questions on the chat, Kasun, if you can.
I can check them, yeah. There's another question on using gRPC with serverless platforms.
Kasun, if you can repeat the
Yeah.
question, would be good for the record.
So the question is, the earlier Go code seems to show a serverless structure to the parameters, context plus payload. Does this imply that when we can lambda with gRPC without an API gateway? Yeah. So basically, the gRPC interfaces that you expose to the external world is purely through HTTP2, right? So because the implementation is bind to HTTP2, therefore it can invoke any gRPC service can be invoked via a HTTP2 gateway, which means if you have a Lambda that can do HTTP2, basically event that you can trigger HTTP2 event, it can invoke the gRPC service. The catch is you have to send the binary format that is required to invoke the service, because at the wire level, it's protocol buffers coming in. So you need to have the correct binary format to invoke it via a serverless function. There's another question on when you start the server, what server it is booting up. Is it similar to serverless? Can we say that it is a lighter version of a streaming service? So when you start let's say you are starting a Go or Java gRPC service. So underneath it will start a HTTP2 server, right? So the inbound traffic to the server is HTTP2. After that, you convert that into a basically unmarshal it into the actual remote method. So this is marshalling and unmarshalling concept in RPC. So basically you unmarshal the incoming remote method invocation to the actual mapping remote method. So basically any gRPC service can be considered as a HTTP2 server. Yeah, so yeah, that's all we have. Yeah.
Yeah, thanks, Kasun. Nuwan, you want to share the screen? So Nuwan, in fact, joining from Colombo, Sri Lanka. It's, I think, 11:30 p.m. there.
Can you see the screen?
Yeah, Nuwan, yeah, we can see.
Okay, cool. To the present now. Yeah, so let me try to quickly walk you through a few samples of using gRPC and microservices. So Kasun, I think, showed you a much more expanded version of this scenario. So ideally what you will have is, you will have several microservices, such as in this case, you will have a microservice that is processing your orders, and another microservice that is updating your inventory. So whenever someone places an order on your retail system, it should update your inventory and update your stocks as necessary, right? So typically this order processing service would be the client facing service, meaning that typically it would be exposed through an API gateway to the outside world through HTTP. But when it receives a request, there will be multiple things that are happening in the backend, such as updating our inventory. So this inventory microservice is kind of like never exposed outside your system. So it will be internal microservice only. So therefore, gRPC makes perfect sense to be used as the protocol for the communication between these two microservices. So let's basically try to see what it looks like. To run a simple gRPC client and a server. So I'll show you a few demos. So I'm using Spring Boot in this particular example. So the samples that I'm going to use are from the book that Prabhat talked to you about in the beginning, Microservices Security in Action. So these are particularly from chapter 8. So I'll run a couple of samples and show you what it looks like. So initially, I have some code that contains a simple gRPC client and a gRPC server. So what I'll do is I'll compile these first and execute. So before actually going into that, I'll also talk about the security aspects of this. So going back into the presentation. So one of the problems with this this communication is that this happens like any microservice that is inside your ecosystem can talk to your inventory service, but this is not what you want to do ideally, right? So you want to make sure that the person which updates the inventory always happens through the one who is supposed to do that, such as in this case the order processing microservice. You don't want anyone else to come and update your inventory. So in case there's a bogus microservice in your system, or if some other microservice unintentionally talks to the inventory microservice and tries to update your inventory, you don't want to allow that. So how do you prevent that? That is by enforcing a mutual TLS between these two services. So you basically, in a TLS kind of scenario, the order processing service will validate the server, in this case the inventory service. But in this case we want TLS both ways, meaning we want mutual TLS. We also want at the inventory service, we also want to validate that it is actually the order processing microservice that's talking to it. So mutual TLS is one way of ensuring this. So we'll walk through a sample of using MTLS for securing the communication between these two microservices. So let me quickly go and compile this. So I have a Gradle command to go and compile this. Hope you can see the screen. Yeah, so so the build is successful. So the next step for enabling or setting up mutual TLS is to create the respective certificates. So if you're familiar with certificates, you will know that there would be a CA who signs the certs, and there would be a server certificate and a client certificate. So I have a script that basically creates these certificates. So on initial execution, it creates the CA certificate, the private key.
And Nuwan, will you be sharing the Git repo of these samples?
Yes, yes, I'll share the link. It's taking a bit of time. So the CA certificate is created, and next the script is creating the server certificate. And finally, it's creating the client certificate. Taking longer than usual, and yes, we should be done. So yeah, The certificates are now created, and I'll now run this client and the server. So first I'll start the server process for this. So this is the command that I'm using to start the server. So as you can see here, I'm starting the inventory server and passing in the variables, the host and the port. So host is localhost and the port goes as 50440. And as arguments to the server, I'm passing in the server certificate, the private key of the server, and also the CA certificate. So by passing in these certificates, I'll start the server. So as you can see, the server has started now. And next, I'll start the client process. So that too is similar. And for the client as well, I'm passing in the same parameters. Let me see, I can't see this for some reason. Yeah, so I'm passing in the host and the port as before, the CA cert, the client certificate, and the private key of the client. So when I start the client will initiate a request to the server, and you should see an inventory update coming in on the server side if this is successful. So as you can see here, we have a message saying the inventory has been updated for one product. So that's basically how you set up MTLS. So just for testing sake, let's try to access, let's try to run the client without without providing its own certificates, like the client certificates and the CA certificates. So if you try to run the client, basically I'm passing in the same arguments as before. I'm starting in the client process, localhost and 50440, and I'm just passing in the CA certificate so that the client can trust the server, but I'm not passing in the client certificate and the client private key to this process now. So the server shouldn't have any way of verifying the client in this case. So if I try to execute this process, you will see that there's an exception and the client cannot connect to it. So this is basically one way of ensuring that the gRPC servers can get requests by trusted clients only. So there's a secondary mechanism, which is by using JWTs. So another way of ensuring this is to make sure that we use JWTs and exchange the JWTs with proper scopes. So in this process, what will happen is a client will get a JWT from the STS, and the client will pass this JWT to the API gateway. So for simplicity's sake, I've just drawn the diagram in such a way that the JWT that is sent by the client is going all the way through to the order processing service. In most realistic situations, this won't be the case. The client JWT will be validated at the gateway, and the gateway in most cases will generate a secondary JWT that the order processing service will use. But for simplicity's sake, let's assume that this JWT is going all the way through to the order processing service. So the JWT that the client obtained here in step 1 is valid to access the order processing service. However, it shouldn't be valid to access the inventory service because the inventory service should ideally require a special scope, a special permission to say I can update my inventory. So how we do that is by exchanging this JWT that we get through the STS for a secondary JWT that has the proper permissions to access the inventory microservice. So what will happen here is that the order processing service will talk to the STS, and since it is this same STS which issued the first JWT, it will by default trust it and exchange it for a secondary JWT that has the permissions to talk to the inventory microservice. So this is basically another way of ensuring the proper authenticated or permitted clients are talking to the respective microservices. So this way, the STS has complete governance over who can talk to the inventory microservice by issuing tokens. So we'll quickly see a demo of what that looks like. So I'll shut down these processes and go to the next sample section. So we have an STS. So for first, what I'm going to do is I'm going to start the STS. So the STS is used to get a token. Okay, looks like the STS is up and running. Right. So next, what I'll do is I'll issue a command, a request to the STS to get a token. So I'm going to issue this curl command. So if you look at this command, it basically passes in a set of parameters like my client ID and client secret. If you are familiar with the OAuth protocol, and I'm passing in some preset password and username of a user called Peter, and I'm sending the request to the STS. So hold on this.
I think the curl command is little malformed. The second line.
Yes.
Mistake, yeah.
Yeah, so I have a token here. It's not shouldn't be very clear. Let me try and copy it into jwt.io just to show you that it's a JWT. So let me quickly paste it over here. So you can see that the token that I got is a JWT. So those of you who are familiar with JWTs will know how to read this. There's a header, and then there's a payload. In the payload, you can see the various claims such as the username, the JTI, the client ID, and the scope. So in this case, I'm just using some random scope called full. So that's basically what the JWT looks like. So now that I have this token, let me set it in my terminal session so that I can use it later. And now I'll basically go and compile my gRPC client and server. So I now have a token. I'll compile this process, and the compilation is successful. I'll first start my gRPC server using this command. So just as before, I'm passing in all of the parameters, the host and the port and the certificate. So the server is started, and then I'll start the client. So one thing to note here is that I am passing in the token as a variable into the client process. So when I'm starting the client process, I'm passing in this token. So let me fix this. Oh, sorry, I'm in the wrong directory. So as you can see, you've got the update message here saying the update, this was the request is successful. So let's quickly try executing this client without the token, and you should see an authentication failure message here saying the request is unauthenticated. So one thing to note here is that, so we are using gRPC's gRPC here. Unlike in HTTP, gRPC clients or gRPC doesn't have a concept of headers. So when this token is being passed, there's a concept called metadata in gRPC, which is like a key value pair. So you basically have to add the token as a gRPC metadata. So if you quickly have a look at this piece of code here. So this is called, this is the gRPC client code. So gRPC, this is Java, by the way. So gRPC clients have a class called client interceptor. So you can have implementations of the client interceptor and execute code that are to be executed just before the clients are sending a request to the server. So in this case, I'm having an implementation of this. And in this client call method, which is getting executed, you can see that we are setting this JWT, the token, into this variable called headers. So headers is basically not HTTP headers. This is a gRPC metadata. So basically anything that you want to pass in that way, such as authorization and stuff to gRPC servers, you can use this metadata like we have done here. So this gRPC client is interceptor is executed just before the client sends the request to the server. And in the same way, on the server side, the server also has something called a server interceptor. So you can have an implementation of the server interceptor and use that on your server side to validate this token. So if you can see here, this intercept call method gets executed just after the server receives your request, and you get your metadata as input into this method, and you can basically extract information from this metadata, such as in this case I'm extracting the JWT from this metadata map and then passing it into a validate method. So this method basically validates against the STS, or in this case it's a JWT, so it can self-validate by looking at the signature. And this way the server can basically validate the JWT and see if it has the necessary permission to access your resources. So that's basically how you set up security for gRPC. So MTLS and JWTs are two ways you can use to ensure your communication is secure. So I'll quickly move into talking about event-driven services and Kafka and how to secure your communications in Kafka. So this is basically what we so far saw is a typical request response based regular microservice architecture, although it was implemented in gRPC. So you will have these kinds of services, like when you are processing an order, you may need to talk to a shipping microservice, you may need to talk to your inventory microservice, and so on. Now, when you're adding more features, so assume that you want to add a new feature into your store to track your buyer's purchasing history, right? So now if you wanted to do that, what you will have to do is you will introduce a new microservice called like buying history microservice and introduce it into your system. But if you can notice, if you notice here, there's a new line that is also being introduced when you introduce this buying history microservice. And when you introduce this microservice, you have to now go and change the order processing microservice to also talk to the buying history microservice that captures your purchasing history. So this is not a very scalable or robust solution, because every time you introduce a new change or introduce a new microservice, you have to keep updating the order processing microservice. Plus, the order processing service really becomes a single point of failure for many of the things. So there there are certain microservices where you really want for them to be synced, such as, for example, the payments. Like, for example, you cannot process an order until the payment is finished. So in that case, the payment microservice could be a synchronized dependency. But in most cases, there would be other functions that you can execute asynchronously offline. So this is where the event-driven or reactive microservice patterns comes into the picture. So how that works?
Before we go there, so there's a question, I guess, related to the previous sample you ran. Does the JWT issued to the order processing service depend on the client or the client request?
Yes, it depends on the client. So the client is the one that is initially, in this particular case, Prabhat, the question was for the order processing or for the inventory?
Issued to the order processing microservice.
Right, okay.
Yeah, so this is the JWT coming. Do you have diagram? Maybe if you go there, it'll be easy. JWT coming from the gateway to the order processing microservice.
Yes. So in this case, this question is about the JWT issued to this particular client. So in this case, for the inventory microservice, the client's JWT is not really relevant, because who is directly talking to the inventory microservice is the order processing microservice. So this client gets a JWT from the STS that has permissions to process an order. Use it through your order processing microservice. So the token that this client gets has permissions to talk to the order processing microservice, but his token cannot be directly used to talk to the inventory microservice. The STS will not issue a token to this client that has permissions to talk to the inventory microservice. What will happen here is a token exchange, where this client's token is exchanged by the order processing microservice to talk to the inventory microservice. That would be the pattern.
Yeah, so the number 3 there, does that token that the ordering process, the exchanged token, depend on the client or the client request, or just the order processing microservice?
It depends on the order processing microservice.
But not the client?
Not the client in this case.
That was the question. Thank you. Okay.
All right. So yes. So going back to the broker pattern. So this is how it would be in a reactive architecture. So what will happen is your client will send requests to the order processing microservice, typically through an API gateway. And for the functions that it can execute asynchronously, what this order processing microservice will do is it will issue an event to a broker. So anybody in the system can listen to events on this broker and take appropriate actions. For example, in the case of buying history, the buying history microservice will listen to the broker for order events and record the purchasing patterns of clients offline. So that's basically how, very briefly, how reactive or event-driven microservices work. So Apache Kafka is one of the most popular open source brokers out there, which can be used to implement this integration pattern. So it has a concept of topics. So topics are basically like channels people, consumers and producers connect to. So producers would produce events and push to these topics, and consumers would listen to these topics for events. And whenever an event is received on a topic, they would act based on what they're supposed to do. So we'll quickly go through a simple sample of Kafka and then see how we can secure the communication channels. So the next sample that you're going to see is a simple client making a request to the order processing microservice, where the order processing service event issues an event to Kafka, and that event is being processed by the buying history microservice. So First of all, let's go ahead and start our Kafka servers. So Kafka also needs a zookeeper for coordination process purposes. So we first need to start the zookeeper process. And once zookeeper is started, you can go ahead and start the actual Kafka server. Start it over here. So as you can see, Kafka, when I started the Kafka server, it goes and registers itself against zookeeper, notifying him that it is present in the cluster. So we now have a Kafka server up and running, so we can execute this command to see what kind of topics we have in Kafka already created. So there's the orders topic. Let me expand this a bit. And execute that command again. So there's this orders topic that's been created in Kafka for this purpose. And this is an internal topic that is used in Kafka. That's not really related to our use cases. So that's it on the Kafka side. So next we have to go and start our microservices. So let's quickly navigate to that. So I'll start our order processing microservice first, and then at the same time also start the buying history microservice. So I'm starting these two microservices, the order processing one and the buying history microservices. So the order processing one seems fine. Right now the buying history microservice is also started. Okay, so next I'm going to send a curl command to this order processing microservice, and if all goes well, the buying history microservice should receive an event and it should be printed in this terminal. So let's quickly go and execute this request on the order processing service. So you can see that the buying history microservice received an event saying it updated the order. It updated its history with this particular order. So this is basically a very simple demonstration of how events work. So let's now talk about how we can secure this communication channel. So let's also try to see if we have. So I try to do a packet capture of this, and let's try to do a new packet capture of this to see if we can see the messages. Yeah, so as you can see, so this is a Wireshark packet capture. So I wasn't using any TLS, so it was just happening. The communication channels were not secured. So as you can see, anyone who has access to this network channel that's happening, network that's between these communicating parties can basically look at what's going on in the system. So in this case, I was using this Wireshark packet capture and listening on this particular port. Should be, yeah, 9092. So as you can see here, the JSON that is going on is visible. So all of the details are visible on the network to me. So this is something that we want to prevent. So to do that, one option is to enable TLS between TLS in Kafka. So basically, you enable TLS, and therefore through that you encrypt the messages that are in the wire. So let's quickly see how we can enable TLS on Kafka. So just as before, in order to enable TLS, you need to create the respective certificates first. So let's go ahead and do that. And before we do that, we'll stop our processes. So I'm running this Docker container from Prabhat's Docker repository to create the certificates. So there's this command, and just like before, it's basically first creating the CA certificate. And then the certificate for the orders microservice. And finally, the certificate for the buying history microservice. So my certificates are now created. So next I have to copy them into the respective microservice directories. So let me quickly go and do that. So I'm now copying the generated certificates into their respective directories. Right. So that's it. And finally, I have to restart my Kafka server now because I've refreshed or regenerated the certificate. So that requires a restart of the Kafka server. So let me quickly go and do that. Okay, so my Kafka server is now started. So let's go and now run our microservices. So yeah, it's in this directory. So let's go to the orders microservice and start our orders microservice, and then do the same thing for the buying history microservice. Yeah, orders one started successfully. And so did the buying history microservice. So, so next step, we have to send a request to the orders microservice to see if this is being captured properly. So I'll quickly go and send a request here. And as you can see, we received this message on the buying history microservice, meaning that we got the request properly. So let's stop this and start. And so we are now listening on the SSL port, and let's see if we can try to recreate the same scenario again. So if we go through the messages in the wire right now, you can see that there's no plain text message. So this is, yeah, this is actually the, sorry, this is the packet that has the message. So basically all of it is now encrypted. You can't see the the actual message or the plain text message on the wire, because it is now being encrypted through TLS. So that's basically how you encrypt the data on the wire. However, so even with this, there's still the problem that we discussed before, the lack of NTLS. So even in this scenario, a bogus microservice could still connect to Kafka and send an event about an order, and your buying history microservice would then go and update itself with false information. So since we use just TLS, anyone who has information about the public certificate of Kafka can connect to it, as long as it has connection capabilities, can connect to it and send events. So even in this case, we want to ensure that it is only the order processing microservice that can talk to Kafka, and the same way for the buying history microservice. We don't want to allow any known microservices to connect to Kafka. We want to ensure mutual TLS between these. So how do you do that? So again, there's some configurations on Kafka that we need to do. Let me see where those are. Right, so one of them is this property called SSL client authentication required. So basically this is, let me try to, yeah. So if you can see here, this is a Kafka property file, the service.property file, the configuration file on Kafka. So it has these three properties saying that you require client authentication, and then the location of your trust store, basically the trust store that contains all of your clients, trusted client certificates, and then the trust store password. So we have to enable these properties, and then of course do a restart of our Kafka server. And so let's quickly go and restart our Kafka server. And at the same time, on the client side, we need to enable similar properties. So this is basically, let me show you. So this is basically the configuration file or a property file of my buying history microservice. So we have to enable these parameters, basically the parameters that tell this microservice where my key store is, and so on, the key store password and the key store type. So because we are enabling mutual TLS, that's both ways. So we have to enable these properties, and the same thing we have to do for the orders microservice as well. So on the orders microservice side, we have to enable these properties that inform it about its key stores. Right, so we then basically have to recompile our microservices since we enabled some new properties on these microservices. Let's go and recompile them. Okay, now let's run these microservices. And if all goes well, they should connect to Kafka successfully when we are running them. Since we've enabled client authentication on Kafka now, it expects anyone that is connecting to it to be a trusted client, basically someone who has the certificates that's in the Kafka trust store. Okay, so looks like our orders microservice started successfully. Yeah, and so did the other one. So let's see if this request still works. Yep, so you can see that we are receiving, when I send the curl request, you can see we are getting this message on the buying history microservice indicating that it works. So mutual TLS now works. The client Kafka now only allows trusted clients to connect to it. So we go to the next section of access control. So we still have a problem with this kind of an architecture, then that is related to authorization. So what happens here is that, as you can see, our order processing microservice was able to write to this topic called orders, and it was a trusted microservice, and the buying history microservice is also a trusted microservice, and it can also connect to Kafka and receive events. However, it can also intentionally or unintentionally write events to the orders topic, because both are trusted at the transport level, at the mutual TLS level, but there's no authorization set up in order to specify who can write to orders and who can read from orders. So this is the next problem that we want to solve, and you can do that by setting up ACLs or access control lists in Kafka. So in Kafka, an ACL is defined in this way, such that a principal P is allowed or denied some kind of an operation O from a host H on any resource R. So might sound a bit gibberish, but if you go through the definitions of this, a principal is basically the entity that attempts to perform the operation. So in this case, our microservices, each microservice, so if you look at the orders microservice is attempting to perform some kind of an operation. So an operation could be things like writing events to a topic, creating topics, deleting topics, and so on. From host, the host is basically the IP address of the principal or of the client that is trying to perform this operation, and the resource is the entity on which this operation is being performed. So in this case, it's a topic called orders, and the pattern is basically the resource pattern is basically what is used to identify the rule, the rule that is to be applied on the particular resource. So if you this will be simplified when we try to look at the look at the example that we are going to execute. So now, first of all, in order to apply an access control to Kafka, Kafka needs a way of identifying a client. So what we are going to tell Kafka is, here in simple terms, is that allow a specified user to perform a specified action on the Kafka resources. So what that basically means is you first need a way of identifying the user. So how does Kafka identify the specific user? So in the previous example that I showed, we used certificates, or we use mutual TLS for the authentication purposes. So when we use X509 certificates for this, right? So when using X50 certificates for this, Kafka identifies the user using the distinguished name of the client. So the distinguished name in this case is basically this whole string. So your certificates, if you're familiar with certificates, you know that the certificates have these attributes, the common name, and so on. So the combination of all of these attributes in a comma separated manner is what is considered as the distinguished name. So Kafka uses this distinguished name to identify the clients. So however, we can override this rule. We can, instead of looking for this entire string, we can instruct Kafka to look for a particular part of the string only. And this is how you do that. You basically say, apply this rule, and and based on this format, so it has like a pattern and the array number or the element number that you want to match, and L or U character, basically lowercase or uppercase character. So what we are telling here in this rule is we are asking Kafka to override its default client identifier mechanism and look for any CN. So look for this particular string only. Look for whatever the string that's in the CN field and convert it into lowercase and use that string as the client identifier. So if you look at this example on the top, what that means is Kafka will consider this string only, like orders.ecom.com string only, as the user identifier. So it will use that as a way of identifying the user. So I hope it's clear how Kafka can identify users now using the details in the certificates. And now this is how you set access control rules. So there's a command in Kafka that allows you to do that. So what you basically say is, so the text in bold here is the important part. You say add allow principal, right? You basically say instruct Kafka to add the rule. And you say who is the user, so you annotate that by saying user colon, and in this case you say bh.ecom.com. so this is basically coming from the certificate, the CN, and what operation you're permitting this user to do. So in this case you're saying user bh.ecom.com is permitted to do read operations on the resource orders. So when we add this access control list or ACL to Kafka, only users with this CN will be permitted to read from the orders topic. So that's basically how you simply apply access control list through Kafka and enforce authorization. So I won't go into a lot of detail on this, but I'll quickly show you how you can add an ACL and list ACLs. So if you want to view the list of ACLs on a particular resource on the orders topic, for example, you can use this command. So this basically says authorized properties, and you give the zookeeper connection URL and -- list and say -- topic, and you specify the name of your topic. So if you execute this command, you will see that there are no ACLs at the moment. So let me go and add two ACLs. So the first ACL I'm going to say allow this the orders microservice to be the producer for the Kafka topic orders. So what that means is I'm saying only the orders microservice can produce events to the orders topic. So if I execute this command, this will now instruct Kafka to only allow the orders microservice to write events to the orders topic. And the second ACL that I'm going to put into my system is to say only allow my buying history microservice to read from the orders topic. So nobody else is allowed to read from the buying history from the orders topic except for the buying history microservice. So that's what I'm saying here through this ACL. And it should get added. And if I now try to list the ACLs on the orders topic, should be visible here. Right, so as you can see here, the orders microservice has permissions to write, to describe, and to create the orders topic from any host, from any IP address. So in this case, the IP address doesn't matter as long as you are authenticated as the orders microservice. You are permitted to do these three operations on the orders topic, and the buying history microservice has permissions to read from the orders topic. So that's basically how you set ACLs on Kafka. And when you do that, the microservice bearing the respective certificates will be permitted to perform those actions. So that's basically how you set. That's one way of setting access controls in Kafka and securing your Kafka topics. But there are a lot of other security mechanisms available in Kafka as well, such as through JWT and so on. So the samples that you saw, you can find these samples in the GitHub repository. So these samples are specifically in chapter 8 and chapter 9 of this book. So you can go to the GitHub repo and try them out yourselves as well. So that concludes my session. I hope it has been useful to you.
Yeah, thanks, thanks, Nuwan. Yeah, so there are a few questions we discussed on the Zoom chat. Any other questions to Nuwan? Let me see. Yeah, looks like we don't have further questions. Okay, thank you very much, Nuwan, for doing this session, and also Kasun. And next meetup, we are going to talk about how to secure gRPC communications in a Istio service mesh environment. Yeah, thanks for joining. Okay, bye.
Thank you.